Welcome to the video on local martingales. So in this video, we want to discuss an extension of martingales, which we have studied in the last video, because if we start, what we realize when we start developing stochastic integration, it might happen that if we have a stochastic integral with respect to a Brownian motion, which itself is a martingale, but the stochastic integral is not a martingale anymore. So the class of martingale is not stable under stochastic integration. And in order to find a stable class, we need to generalize the notion of martingales to local martingales. Okay, so as usual, we have some underlying filtration, right? If you talk about the martingale filtration popping up, and of course we have a complete underlying probability space. So in this section, this will be always filtration. And here, well, for simplicity, we assume that it satisfies the usual conditions, right? So the filtration is complete and right continuous. The usual conditions. So let me start right away with the definition, what a martingale is, so that we all know about what I'm talking about. So this is definition 2.16. So what we want is, okay, we consider an FT adapted process, okay, a stochastic process, XT, as usual, and we call it a local martingale. If there exists a sequence of stopping times such that the first thing we want is that this sequence goes to the terminal time t, and if the terminal time t is infinity, this means just the stopping times go to infinity, and this of course p almost surely, and we want that process xn, which is given by the stop process xn minus x0 is a martingale. Martingale for all n. Right. So if we stop, if you look at the stop process xt tau n, then this process becomes a martingale. Right? So if we have a sequence of stopping times, in the sense localizing the martingale, then when the localized process is a martingale, then we talk about a local martingale. And if you, this x0 is a constant, you can just look, you can forget about this term. So if this is a constant, you can cross it out. So this is just to give you the general definition that you that you don't care about the integrability at x0. Okay. All right. And now the corresponding sequence here of stopping times is called localizing sequence. Okay, and then we have in the same spirit, you can define local sub and local super martingales. Okay. Are defined right. So this means, I mean, if you have a local super martingale or local submartingale, this means there exists such a sequence of stopping times so that the stop processes are local, are super martingales or submartingales. Okay. Let me keep it in green so that you can better find it. All right. Okay, so first thing I would like to do is to give you an example of a local martingale, which is not a martingale, right? Which is, okay, you might wonder if this is really a bigger class or not. I mean, okay, of course, every martingale is certainly a local martingale because, well, you can just take the sequence of stopping times tau n just to be a capital T. Then you're done. So let's come to the example of a true local martingale in the sense that it's not a martingale, but it's a local one. Okay, so how I mean, there are several constructions you can find if you look around of examples. So this is just one. So we start with the Brownian motion on the interval 0 to infinity. Brownian motion. And I would like to introduce the stopping time, which is called capital T minus 1. So capital T minus 1 is just the first time such that the Brownian motion hits the level minus 1. Just keep in mind the Brownian motion starts from 0 and it's a continuous process. So it doesn't, I mean, this is not 0, but I mean, at some point, the Brownian motion might or might not hit minus 1. And okay, one can actually show that it will always hit minus 1 almost surely. Okay. And then we can define the process xt, or I would like to define the process xt as the Brownian motion t with the time index replaced by t over 1 minus t, and then minimum with the stopping time t minus 1. So this is what I do for 0, if t is between 0 and 1. You see, I mean, this process at time 0, this is just the process starts from 0. And then here I twist a bit the time. And I mean, basically cut off, stop the process if I hit the level minus 1. And of course, this is not well defined for 1. So for the time 1, I just assume that it's, I mean, I set it to be equal to 1. And the time is twisted in a way that if I approach 0, this goes to infinity. So this term here. So this will at some point hit minus 1. This is again a continuous process. So I'm not giving you here all the details because what I want to give you an idea how one can find a local martingale, which is not a proper one. So this is a continuous process actually. Okay, it's a reciprocity, that's true, but I want to make the statement this is a local martingale. And I want to make this second claim that this is not a martingale. Right? Okay. So how do we see that it's not a martingale? This is, let's start, okay? Next T is, so this is the first statement, is not a martingale. martingale. Well, if we have a martingale, this means the expected value of xt has to be constant, constantly to be equal to the expected value of x at time 0. So let's calculate it. If you look at the expected value of xt, well, what is it? If I'm in the first case, so if t is equal to 0, between 0 and 1, well, this is just equal to 1, right? Because the stop Brownian motion, I mean, this is just a Brownian motion at a certain time, right? If it's this has to have the expected value. This is a martingale, so it has to have the expected value of b0, and b0 is equal to 0. So let me write this down as t through t as 1 is a martingale, right? So I mean, this just looks a bit weird because I twisted here the time, but this just means here the stop process is a martingale. This is a martingale. Okay, but if I look at time t equal to 1, well, certainly, I mean, the process is constantly equal to -1, so the expected value has to be -1, right? So this cannot be so xt cannot be a martingale. Okay, the second claim is, but it's a local martingale. Is a local martingale. Right? Indeed. So if we want to show that it's a local martingale, and this means we need to find a increasing sequence of stopping time. So the sequence of stopping goes to 1, in the case of the example, such that the stop process is a martingale. So what we do, we introduce the localizing sequence, which is the first time t one at infinity, such that my process x hits the level 1, hits the level n, and minimum 1 for all. Okay. Okay. So what have I done here? Right, the process is bounded from below by -1. Okay, and it's now, since it's a continuous process, it's also bounded from above by n if I stop it with tau n. So this is the standard trick, as you also see on the exercise problem sheets, to find a localizing sequence, right? You want to bound the process because then you have usually dominated conversion at hand to make sure that this is a martingale. And my claim is now this is here a localizing sequence. So this that's the job, right? So what I want to show is so if the n goes to infinity, let me make the first statement. This goes to T1. Right? Because I start from 0, and if I make the bound higher and higher, this will go to 1. And what I also claim, I mean, I would not give you all the details. This here is a martingale. For all n. Why? Okay, first let's check the problem with the expected value, right? If I look at the stop process, the expected value of xt minimum tau n, if I'm before time 1, this is always 0, so that's fine. So the only thing we need to ensure is if I look at x at time 1 and minimum tau n for every n, well, the good thing is now I can use dominated convergence, right? So I can sneak in here an expected and then limit of k equal to infinity of k over k plus 1, right? This is just approaching 1, minimum tau n. And here since I bounded it, since my process is now bounded by -1 and by n, I can use dominated conversion. And dominated convergence tells me I can pull out the limit. I have x times x plus 1 minimum tau n, but this is 0. So everything is equal to 0. And that's great. So I mean, I have now an integral process which is adapted and the expected value is constant. And now I can apply the same argument for the conditional expectation. I will not spill it out. Apply the same argument to the conditional expectation. To get, well, what do we need to get as usual? Right? You look at what you have to show is this. And the same dominate conversion arguments goes through but for conditional expectation. So what you get is exactly the Martingale property. Oh, this has to be an S. All right. Okay. I mean, okay, I dropped some details, but I mean, this is just to convince you that this sequence here is always a local Martingale. Maybe I should really include that. Okay. N is called localizing sequence. Right. Okay. Cool. And the nice thing about local martingales is that, I mean, all the results you in some sense have seen for local true martingales, I mean, they extend to local ones by just introducing the localizing argument sequence. All right, so let me give you some properties, which is presented in proposition 2.18. Okay, so we take a local martingale, which is assumed to be continuous to make our life easy. Be a continuous local martingale. Okay, can also, yeah, you know what I mean, local martingale. First claim is, right, if I if tau is the stopping time, then the stop process, call it y, is a local martingale. Okay. So this is the same as we had seen for optimal optional stopping, right? If you have a martingale and you consider the stop process, then it's still a martingale. And here we have, if we have a local martingale, if you introduce the stop process, it's still a local martingale. If our process X is bounded, some constant B. So I mean, this means for every time I'm uniformly bounded. So this holds for all t. All t. Then it's actually a true martingale. Okay. And the last thing is if X is non-negative, it's bounded from below only, and I assume that at time 0 I'm integral. The reason is that, okay, for the local martingales, we are not assuming any integrability time 0. So let's do this. Then X is a super martingale. So the statement, if I'm bounded from below and above, then I'm a martingale. If I'm only bounded from below, I'm a super martingale. Okay. So let's prove this. It's not hard. It's just running through the definitions of a local martingale. Okay, first thing, you can always subtract the initial condition. So we assume that the initial condition is just 0. And now let's assume here we have a localizing sequence. Sequence 4x. Okay, what's the first thing? Okay, if we stop, then we still have a martingale. Well, okay, if you look at the stop process, let's say, what we need to show is that this here, right? If I look at the stop process here, this is, I mean, if I localize it, this has to be martingale, right? So we want to show that Y is a local martingale. This means if we apply our localizing sequence, then it should be a martingale. Okay, that's easy. So just recall the definition. Right. Okay. Can I also make t's tau? And here I have forgotten tau n. Here we go. Here's tau n. So what is it? This is nothing else than tau minimum t, and then stopped with respect to tau. Right? And this is a martingale. Is a martingale, as we know that x t tau n is a martingale. And then you can apply optional sampling. Optional stopping, sorry. Right, this is just iterating this stopping process. So the point is, since tau n is a localizing sequence for x, the stop process is a martingale. And if I stop a martingale, so I look at the stop process of a martingale, this is still a martingale by optimal sampling. So this is a martingale. Okay. was the second claim. Okay, I want to show that if I have a bounded local martingale, then it's even a true local martingale. Okay, what do we okay? We have to check three things. The first thing is that it's adapted. That's clear because the underlying process was adapted. That a local martingale has to be an adapted process as well. So we only need to check the integrability. Here we go. Since the process is bounded by B, also the expected value is bounded by B. Oh, yeah. Okay, that was fairly easy. So we need to show show the Martingale condition. So we want to show this. The conditional expectation of xt given ft is t. Well, but we know that this holds already true for the stop process with respect to tau n, right? So this is given by the definition of a local martingale. And now we can use dominated convergence because we have a bounded martingale here, a local martingale. And convergence theorem we get. And so we want to show star, I mean, not star, we want to show this here, right? So we do the same. So we want to show if we take and set A, well, actually want to show it for all A and F. This is just the definition of conditional expectation, right? And we want to show that this is equal to the expected value of x at time s multiplied with the indicator function of A. And then, as I promised you, we want to use dominated convergence. So we approximate xt again with xt minimum tau n, right? And the sequence of stopping times goes to capital T. So this is, I mean, the limit f xt. And now we use the dominated convergence theorem, which here, this is where we use domination convergence theorem to pull out the limit. Now then we have the stop process of x multiplied with xn. And now we know that this is a martingale here. So we know that, okay, we keep our limit tau to infinity of s minimum tau n, right? Because we know that the stop process is actually a martingale. And this means, well, this is nothing else. If you pull in the limit again, here we go. This is xs given as t. And this is what we wanted to prove. Okay. So the proof is actually, I mean, here everything is simple. You just need to familiarize yourself with the definition of a local martingale. So the idea that you have a local martingale is basically a martingale if you find a localizing sequence. And then you always work for each n. So with the localized process, because it's a martingale, and extend it to the local martingale. And since I said it's not hard, but you need to familiarize with the definition, the last question is left for you as an exercise. Okay. And another thing which I'll leave you as an exercise is actually something very useful, and we will apply it quite often, is the fact if we have a local martingale, a continuous local martingale, which is a finite variation, then it's almost surely constant. Okay, so you have a local martingale, and yeah, you have, I mean, done it as an exercise, and now you can extend it again by the localizing argument to local martingale. So you hopefully know this statement already for martingales. and you hopefully means it was in the lecture and you hopefully proved it on the problem sheets. So what I want to say here, this also extends to local martingales. If you have a continuous local martingale of finite variation, and we assume that x equals 0, and then we know that the martingale itself, I mean, this is equal to 0 for all t. Okay. Okay. Again, I mean, you take the results for Martingale and extend it with this notion of localizing sequence. So proof is left as an exercise. You use localizing sequences, which allows you to use dominated convergence. Well, sequence localizing sequence and for x and the lemma where we show exactly the same result for martingales instead of local martingales was 2.14. Okay. Okay, so we wanted to, I mean, the reason why I wanted to introduce this slightly more general class of processes, local martingales, was that I can apply it, or that I needed for the stress integration theory. And I also wanted to, I mean, introduce the notion of quadratic variation, because I told you, okay, this is some fundamental building block of quadratic of stress integration, which is the quadratic variation. And now I want to extend the results about quadratic variation as well to the local class of local martingales. This is the contents of the next theorem, which is 2.20. So okay, let us consider process X as 4, which is supposed to be a continuous local martingale, right? A continuous local martingale. Then there exists, okay, let me write it out. There exists unique, I mean, this is what it's new, so let me make it light blue. And so this is actually new compared to the statement we have seen. But we could have already proven it in the first version for this theorem for martingales. Continuous. Continuous. Process. Called this bracket process, which we called already quadratic variation, and we will later call it quadratic variation as well. So there exists a process bracket X, which has the following two properties. The first one is, okay, it starts from 0 and it's non-decreasing. Decreasing. This is the first, okay, actually these are two properties. And the second one is, if I look at x to the power 2 and I compensate it, so I subtract the quadratic variation, the bracket process xt, then this is a local martingale. Continuous, right? Because both processes are continuous, local martingale. Okay, so this is, yeah, and actually we know how this process, the bracket process looks like. Furthermore, this looks wrong. This bracket process xt satisfies or is given basic by the limit of the sum of square increments. Right, so you take a zero sequence of partitions pi n, and then you sum up all the square increments, and this limit holds in probability for t in 0 to t. Okay, where n is a zero sequence, so any refining sequence of partition which mesh size going to 0. Sequence of partitions. Okay. Right. So let me prove this again. I mean, for the existence part, so I mean that there is such a process, continuous process with these two properties. I mean, there's nothing left to do than applying a localizing sequence. This time I tell you which one. And then applying the corresponding results, which we have seen for Martingales. So existence and claim properties. Okay, how do we do? Okay, we apply proposition 2.15, which is exactly the same statement just for Martingales, and the localizing sequence. And defined, right? Because in the proposition 2.15, we assume that the Martingale given is bounded. Right? So we need to choose a localizing sequence of partition which ensures that everything is bounded. And this standard trick, at least for continuous martingales, is to say, well, I look at the infimum of 0 to t, and I stop the moment my process gets greater or equal, I mean, in absolute values than n. And this is something you can always choose as localizing sequence of partition. Also, if you, for example, want to prove this theorem, right? You can explain exactly the same localizing sequence of partition. Okay. And that this is indeed a localizing sequence of partition is part of the exercise sheet 2. Okay, so the new thing we need to prove here is actually, so this is the existence and but the uniqueness, we haven't done the uniqueness part yet. So I need to convince you that uniqueness works. Here we go. So how do we see uniqueness? Okay. First standard trick I do is I assume that my process x0 is start set x0. And now suppose there are two processes with the properties I and y. So suppose y and z are continuous processes satisfying property I plus property 2I, right? So I have two processes, Y and Z, which start from 0, which are non-decreasing, and if I subtract them from, if I subtract them, if I consider the process x squared subtracted by Y or Z, this is both the Martingale. Okay, cool. So why are Y and Z the same, right? We need to show that they're identical. And this is not too hard. So we look at the difference and we want to show that the difference is 0. If I look at the difference, or I sneak in my x squared. I sneak in my x squared, and then, okay, I have minus Z. Minus square minus Y. Okay, here we go. Right, I just sneaked in. So the x are canceling, Z is minus, Z is here, Y is plus, minus is plus, so this is Y. Perfect. And now I know this is a Martingale, or local Martingale. Yes, a local Martingale. And this is a log Martingale. So it's a local Martingale. So the difference is a local Martingale as well. And it starts from 0. Well, this is by assumption true. Plus, it's a finite variation. Finite variation. Right? So if I look at the difference, Y minus Z, and I want to estimate the finite variation, I mean, these are two increasing processes, so I can use the triangle inequality to estimate it by Y at time t and Z at time tz, and these are finite processes, so this is finite variation. And then we can apply the previous lemma, which is 2.9, so the one which tells you if I have a local Martingale, which is of finite variation, it has to be identical to 0. So this means minus that. Is equal to 0. And this completes the proof. Here we go. Cool. So the quadratic variation bracket process is indeed a unique process with these two properties. So let's make this now to the definition. I mean, we have already talked about the quadratic variation of Martingales. So let me introduce it now for local Martingales. This definition 2. So the process T, the recursive process, and X is the local Martingale. Given by here the limit along any sequence of 0 partitions, 0 sequence of partitions, so the limit is taken in probability for any t between 0 and t. So where n is a 0 sequence of partition, of partitions is called local quadratic variation. So this is just the generalization of the notion of quadratic variation, which we have already seen from Martingales. Oh, let me make it green again. Wow, okay, that's fine. Sorry. Here we go. And this here, the x, right? X is a local continuous Martingale. Okay. Okay, one remark, and then we apply to Brownian motion, because this is our first aim we want to consider, namely the Brownian motion as the main example of a Martingale. So remark, I would like to, show you by how the quadratic variation behaves under stopping. So I have still my local Martingale, and what I convince you is that if I have a stopping time, which is almost surely finite, let tau be almost a finite stopping time, then I have the following identity. So if I look at the quadratic variation of the stop process tau n, so yeah, right, tau n is nothing else than, we have introduced this. This is nothing else than the quadratic variation of the graph x. So the quadratic variation of the stop process x tau is equal to the quadratic variation of x stopped at time tau. Right? I mean, if you look at the definition, this is rather straightforward to guess, because we just say, okay, and I'm cutting off here my square increment anyway. It doesn't matter if I do it here or the process itself. But you can also see it from the uniqueness directly, right? So since tau, so if I look at this process, this fulfills the first property, right? It's the process which starts from 0 and is non-decreasing, because the quadratic variation of x is not decreasing. And well, if I look at square and the stop process, this is a Martingale as well, or a local Martingale. Martingale. And then this means uniqueness of quadratic variation implies that we have the identity which I claim. Because this process fulfills also property I and the second II. As I mean, this is by the different quadratic variation, but now the stop quadratic variation fulfills it as well, so they have to be the same. Well, not that. Okay. So it's just, I mean, so you can like basically pull in and pull out stopping times from the definition of quadratic variation, from the construction of quadratic variation. All right, and now the last thing I want to do in this part of the lecture is to apply the results we had just have derived to the Brownian motion. And this is context of corollary 2.23. So let us consider the Brownian motion, as usually denoted by B, is a Brownian motion. And now I know what the quadratic variation is. So the quadratic variation of the Brownian motion at time t is just given by t. And this is what we know given by the square increments of the Brownian motion along any zero sequence of partitions. So J_t, the Brownian motion square, and this holds in probability for all t and 0 to t. And this is, again, as usual, where the pi n's are supposed to be a zero sequence. Zero sequence of partitions. Okay, so why is this a simple corollary? Well, we just need to use all the results we already know. We know, okay, B itself, so the Brownian motion, and the Brownian motion to the power 2 minus t are continuous martingales. Right? I mean, continuous by definition of the Brownian motion, and what that there are martingales is what we have shown already on the problem sheets for C exercise 2.8. Yeah. So we know that they are Brownian motion, and in particular the process and the process, if I look at the process t mapping to, well, t, right? This is an increasing function, is or non-decreasing starting from 0. Non-decreasing. Okay. So the function t, so the identity function of t, fulfills all the properties of quadratic variation. So by uniqueness, this has to be the quadratic variation. So hence, by lemma theorem 2.20, this is the one about quadratic variation of local martingales. We have first that the quadratic variation of Brownian motion is indeed equal to t, and let's make star holds. So star holds true. Right? This is the second claim we have in the Theorem 2.20, that okay, the quadratic variation is indeed given by this limit of the sum of square increments of the local martingale, which is here just the Brownian motion. Okay. Last thing, let us look. So let's numerically check this. Which you also invited to do yourself. So first thing, let us sample three sample paths of a Brownian motion. Okay, let me make it a bit smaller here. So what this is, if you sample a Brownian motion, 3 sample paths, this is what you might end up with. And so here. And now let's look at the corresponding quadratic variation for these 2 sample parts by taking finer and finer partitions. So if you start with 100 100 discretization per unit. So if you discretize the interval 0 to 1 with 100 small intervals, then this looks always like a straight line. And then you can make this partition finer, go for 1,000 sub-intervals of the intervals of the unit interval 0 to 1. Right, this is what you get then. And right, it's getting closer and closer to the identity function. And if you then, in the last step, go to 10,000, and you see, I mean, it's basically already a straight line. So you see, this is what you get. If you really start numerically calculating here the square increments of a Brownian motion for finite sequences partitions. You cannot play around. I mean, this gets closer and closer to the straight line t equal to t. All right. I hope you enjoyed the video.